Imagine a world where the scientist making the next massive breakthrough in renewable energy isn't a human. Like,
Right.
they aren't wearing a white coat. Instead, it's an artificial intelligence. But we aren't talking about just a static program analyzing data after the fact.
No, definitely not.
We're talking about an AI reasoning in real time, executing physical experiments 24/7, and literally arguing with itself in its own internal logs about the results.
Which is wild to actually read.
It is an AI holding the keys to a robotic chemistry lab. So, welcome to today's Deep Dive. We are exploring a truly fascinating January 2026 preprint from the University of Liverpool titled, Can We Automate Scientific Reasoning in Closed-Loop Experiments Using Large Language Models?
It's a bit of a mouthful of a title.
It is,
Yeah.
but what we are looking at is a hybrid framework they built called BORA, and the results are honestly going to change how you view problem solving.
It's a massive leap forward.
Yeah.
Because what we're looking at here is the transition from mere automation,
Uh,
which is just, making a repetitive process happen on a loop, moving from that to genuine autonomy.
And autonomy is the key word here.
Exactly. Autonomy means the system actually has the agency to make decisions, to adapt to failure, and pivot based on live feedback. That distinction is going to be the engine of future scientific discovery.
Okay, let's unpack this a bit because setting the stage here is really important for everyone listening. We already know automation is great. We have incredible robotic workflows right now that can run complex physical experiments all day and all night.
Yeah, the hardware is amazing.
But there is a bottleneck, and ironically, that bottleneck is us. It's human decision making.
The slow part of the loop.
Exactly. If you have a robot run 100 experiments overnight, a human still has to come into the lab the next morning with a cup of coffee, look at all the results, figure out what went wrong, and then design the next 100 experiments.
Well, the multi-million-dollar robots are basically just sitting there.
Yeah, just waiting on our human brains to catch up.
That is the exact problem this paper tackles. Traditionally, the way laboratories have tried to solve that bottleneck in these closed-loop robotic systems is through something called Bayesian optimization.
Okay.
We'll just call it BO for short. It's a highly effective mathematical method for guessing the next best experiment based on previous data.
So it's an algorithm.
Right, an algorithm that constantly balances exploring new unknown areas with exploiting the areas that are already showing good results.
Mm-hmm.
But BO has a fundamental limitation. It lacks an ontology.
Okay, I've heard that term thrown around a lot in AI circles. For someone who isn't a computer scientist, what does lacking an ontology actually mean in this context?
It means the mathematical model doesn't actually understand what things are.
Give me an example.
Let's say your robotic lab has 100 different chemical dyes it could use in an experiment.
Yeah.
Bayesian optimization just treats them as 100 separate random variables.
Like X1, X2, X3.
Exactly. It has to test them one by one to see how they affect the outcome. It has absolutely no concept of what a dye actually is in the physical world.
But a large language model does.
Yes. An LLM has been trained on vast amounts of human knowledge. It possesses an ontology. It knows what a dye is, what a solvent is, what a salt is.
And how they generally interact.
Right, based on all of recorded chemistry, it knows how they react to light or heat.
So it brings actual context to the math. And this is why, whether you are managing a massive team, trying to optimize a complex business process, or you're just insanely curious about the future of tech, this deep dive is for you.
Because the applications go way beyond just chemistry.
Absolutely. We are going to reveal how machine reasoning is fundamentally changing how we tackle complex problems in the real world. So to really grasp how big of a deal this is, we have to look at the actual tests they ran.
The benchmark arena.
Yeah. They set up two distinct arenas for their hybrid framework. One represents what we could call messy chemistry, and the other represents clean physics. Can you break down the messy chemistry test for us?
Certainly.
Mm-hmm.
Test 1 is a highly complex 10-dimensional problem. The goal of the simulation is to maximize the rate of hydrogen production using a photocatalyst in water.
Okay, so making hydrogen.
Yes, and you've got 10 different variables the AI can manipulate. Things like the amount of the catalyst itself, 3 different types of dyes, various bases, salts, and surfactants.
That is a lot of moving parts.
It is. And the maximum possible optimal score, so the highest hydrogen evolution rate possible in this setup, is just under 30 micromoles per hour. The paper describes a specific chemistry problem as non-convex.
Hold on, non-convex. What does that actually mean for someone who isn't a mathematician?
Imagine you are dropped into a massive pitch-black mountain range. and your goal is to find the absolute highest peak.
Okay, I'm blindfolded in the mountains.
Basically, you start climbing a hill, you reach a summit, and you think, great, I'm at the top. But because it's dark, you don't realize you're just on a small foothill.
Oh, and the true summit is actually like 10 miles away across a deep valley.
Exactly. That's a non-convex problem. It is full of deceptive peaks and valleys, full of unknown interactions at multiple scales. Changing the pH of the water might suddenly change how a specific dye behaves, creating a totally unexpected result.
That sounds like a nightmare to optimize.
It usually is.
And then we have test 2, which is the clean physics. This is a simulation of the game pétanque.
Which is a brilliant contrast.
Yeah, for anyone who hasn't played it, it's that game you play on a sunny afternoon where you throw a heavy metal ball to land as close as possible to a small target ball. The perfect score here is 100. How does this compare to the dark mountain range?
It's the complete opposite. The pétanque simulation relies entirely on classical projectile theory. We know the exact rules of pitch, yaw, velocity, spin, and drag.
So the physics are solved?
Right. It's a 7-dimensional problem, but it's completely precise. If you change the throw velocity by just a fraction of a meter per second, or the angle by a tiny fraction of a degree, the score changes predictably but dramatically.
So it's highly sensitive.
It's very. It's a knife-edge optimization problem. It requires intense precision, rather than navigating unknown, chaotic interactions.
I want you, listening to this, to think about your own daily problem solving. Are you dealing with messy chemistry-like human behaviors, shifting markets, and unpredictable variables that suddenly change how your team works?
Or are you dealing with clean physics?
Right. Hard data, fixed rules, and precise inputs where one small error throws off the whole spreadsheet. Because the AI framework handled both, but the way it won is wild. Let's get into the battle of the bots.
The fun part.
I know they tested a bunch of different models to see who could run the lab best.
They did. The researchers tested OpenAI's O4 Mini, O3, GPT-5 Mini, and the full GPT-5 alongside Google's Gemini 2.5 Flash.
A heavy lineup.
And they pitted all of these against that traditional math-only Bayesian optimization we talked about earlier.
And what were the results? Who took the crown?
The hybrid approach, so combining the LLM's conceptual reasoning with the mathematical rigor of BO, substantially outperformed the traditional methods. What the LLMs provided was a warm start.
Let's define warm start so we're all on the same page.
A warm start simply means you aren't starting from zero. Because the LLM already understands chemistry and physics conceptually, it could form highly educated hypotheses right out of the gate.
So it avoids entirely random guessing.
Precisely. It looked at the variables and essentially said, based on my knowledge of physics, I should probably throw the ball roughly this hard.
Wow.
In the pétanque game, the traditional math-only method really struggled with that knife-edge precision. Over 20 runs, the traditional algorithm was barely scraping a 50% success rate. It never once hit the perfect score of 100.
Not even once.
Nope. But when they paired it with the O3 model, the average score skyrocketed to 98.2 out of 100.
That is insane. It essentially solved the game almost every single time.
Yes. Across the board, the O3 model delivered the strongest, most consistent performance.
But my absolute favorite part of this whole paper is what happened when they took the training wheels off.
The LLM only runs.
Yes. They wanted to see what would happen if they stripped away the Bayesian optimization entirely. No heavy math, no algorithm helping it guess. Just let the large language model run the physical lab entirely on its own.
And it performed brilliantly, but only under one very specific condition.
The batch size.
The batch size had to be small.
Explain the batch size finding to everyone, because this blew my mind.
When they gave the O3 model a batch size of 1 meaning, it designed one single experiment, ran it, looked at the result, reasoned about it, and then designed the next one. It was a superstar.
With no math help at all.
Without any Bayesian math at all. Hitting the problem purely with language-based reasoning, it averaged an almost perfect score in the chemistry test. It hit 27 out of 28.37. It found the absolute optimum hydrogen rate in 15 out of 20 runs.
But what happens if they increase the batch size?
If they force the AI to design 10 or 20 experiments at a time before seeing any results, its performance plummeted.
Wait, hold on. If I have a robotic lab that is capable of running 100 experiments at once, why would I limit it to just one at a time? Doesn't that defeat the whole purpose of having automated robotics? Why slow the machine down?
Because it forces us to rethink what efficiency actually means when you introduce reasoning.
Okay, how so?
If we connect this to the bigger picture, this finding is profound. It tells us that continuous active machine reasoning learning from every single distinct failure, step by step, is infinitely more powerful than processing large batches of data all at once.
Like agile methodology in business.
Exactly. Failing fast and iterating. When you force the AI to design 10 experiments at once, it exhausts its foundational knowledge. It guesses 10 things, but it can't learn anything until all 10 are done.
Right.
But when it runs one experiment, observes the specific failure, adjusts its mental model, and tries again, it out-navigates the pure mathematics. It acts like a meticulous human scientist.
It's like cooking. If you're making a complex soup, tasting it after every single pinch of salt, every dash of pepper, and adjusting based on that specific taste is going to give you a much better soup than just throwing 10 ingredients into the pot at once, waiting an hour, and hoping for the best.
That is a very apt analogy, and because the LLM has that ontology we discussed, that understanding of what the ingredients actually are, it can generalize from a single failure.
Meaning, if it tests one dye and it fails.
It doesn't just cross that single dye off the list.
Yeah.
It stops and reasons, okay, this dye failed.
Yeah.
Dyes might be interfering with light absorption in this specific water mixture.
Yeah.
Let's avoid the entire class of dyes for now.
That's incredible. Traditional algorithms cannot make that deductive leap. They would just blindly test the next dye.
Heck, exactly.
Which brings us to arguably the most entertaining part of the entire deep dive. The sabotage.
Yes, the bad advice test.
The researchers deliberately tried to mess with the AI to see just how robust its internal reasoning was. They essentially injected human hypotheses into the starting prompt that they knew were completely factually wrong.
They did. For example, they explicitly told the AI addition of dyes will increase hydrogen production.
Knowing full well that dyes ruined the reaction.
Right. They also told it that adding bases would be bad and that the amount of the catalyst should be kept extremely low. They were feeding the AI the exact opposite of the optimal recipe, framing it as expert human guidance.
And how did it handle a human actively lying to it? Beautifully. Because it was reasoning step by step, it actually caught the lies. Can you share what happened in the internal logs?
Looking at the logs for the O3 model is fascinating. You can read the AI's internal monologue working through the problem in real time. After a few single batch runs, the AI noticed that the physical data was collapsing every single time it followed the human advice to add dyes.
So it didn't just blindly keep following orders.
No, it reasoned its way out of the human error. In its internal summary log, the AI explicitly wrote, dyes and surfactants virtually eliminated after iteration 3, owing to consistent performance collapse.
I love that. It basically looked at the prompt and said, I don't care what the human told me. The physical data says the human is wrong, so I'm ignoring them.
That is real autonomous reasoning.
So it's smart enough to catch a human lying to it. But what happens when the human isn't lying but is just outdated? That brings us to a major vulnerability the researchers found, which they call the literature trap.
This is perhaps the most crucial warning in the entire preprint. The researchers gave the AI a real, peer-reviewed 2020 publication from a major journal about this exact chemistry experiment.
A good, solid paper.
Yes, and in that 2020 paper, the human authors stated that adding salts, specifically sodium chloride, had a very small effect and was ultimately deselected from their optimal mixture.
Okay, so because the AI read this paper and knew it was from a reputable source, it trusted it completely. It avoided salt.
But there's a catch.
A big one.
The simulation the AI was running in 2026 was built on much newer, broader data. And that newer data definitively proved that salt actually is highly beneficial to the reaction under the right circumstances.
But the AI completely missed it.
Because it anchored itself to the old paper.
This is such a massive takeaway for anyone listening. Giving the AI this good, established literature actually hurt its long-term performance.
It achieved a great warm start because the paper gave it decent baseline parameters, but it plateaued well below the absolute maximum score.
It was too trusting of the old paper and insufficiently explorative. Because the 2020 paper said skip the salt, the AI essentially refused to test salt again, completely missing out on the optimal recipe.
It's the exact same trap human experts and business leaders fall into all the time. Trusting precedent over raw exploration. You have to ask yourself, how often do you let established best practices, legacy code, or the classic way we've always done it mentality stop you from testing new, potentially optimal solutions?
Exactly. The best practices of 4 years ago might literally be the very thing holding you back today. If the environment has changed or the data has expanded, treating an old white paper like gospel is going to cap your success.
Very well said.
Now, speaking of following rules, we have to talk about executive orders. The researchers also tested how well these different models follow strict, non-negotiable commands. They gave the AI a hard rule: do not add dyes. Just completely explicitly told it to avoid them at all costs.
And the results varied significantly depending on the underlying architecture of the model.
How so?
Well, the GPT-5 model was incredibly compliant. It obeyed the do not add dyes order 10 times out of 10 runs. It never wavered.
Good soldier.
Right. But other reasoning models, like a 4 Mini and even the highly successful O3 model, actually forgot or ignored the rule halfway through the experiment.
Wait, really?
Yes. They would start off complying, but as they got deep into the problem-solving iterations, they would suddenly suggest a batch containing a dye.
Why does that happen? How does an advanced AI just forget the boss's top directive?
It comes down to how these models manage their attention over long context windows. When a model is reasoning step by step through a highly complex, non-convex problem, it is generating massive amounts of internal text.
Because it's debating with itself, analyzing numbers, forming new hypotheses.
Exactly. And as that internal log gets longer and longer, the initial prompt, the executive order, gets pushed further back in its memory.
Ah, I see.
It gets so focused on the immediate micro problem of balancing the pH or adjusting the catalyst that it loses sight of the macro constraint. It literally loses the forest for the trees.
Which proves that while these models are brilliant at dynamic reasoning, maintaining hard constraints over long, complex chains of thought is still a real technical hurdle. You can't just set it and forget it if the rules are absolutely critical.
You still need oversight.
Exactly. Now, before we wrap up, I want to pivot to the real-world cost here. Because we all know AI, especially these heavy reasoning models, uses an enormous amount of power. Did the researchers actually measure how much energy this AI burned through to solve these chemistry problems?
They did. And it is a metric we have to take seriously. They calculated that a single, complex LLM optimization run, meaning one full simulation using the heavy GPT-5 model, consumed an estimated 1,045 watt-hours of energy.
Just to put that in perspective for you listening, 1,045 watt-hours is roughly the equivalent of running a standard domestic microwave oven on high for an entire hour straight.
That's a lot of heat.
Just radiating heat. That is not an insignificant amount of power for a computer just to think about a chemistry problem.
It is a substantial energy draw. However, we have to look at the operational efficiency of the entire system. We have to compare the AI's energy cost to the energy cost of the physical laboratory it is operating in.
Right, zoom out.
A standard laboratory fume hood, which is essentially a giant industrial ventilation system required to keep human chemists safe from toxic fumes, consumes about 26,904 watt-hours a day.
Whoa!
And it uses that much power, whether it's actively venting a reaction or just sitting there running in an empty lab.
Wait, so one single fume hood in one single day is using roughly 25 times more energy than the AI used to solve the entire problem.
Exactly. The researchers point out that in a typical 8-day physical chemistry experiment, the energy used by the LLM queries would only amount to about 2% of the energy consumed by just one of the fume hoods involved in the process.
That's incredible.
And that 2% doesn't even account for the electricity used by the robotic arms, the analytical instruments, the heating plates, or the human scientists commuting to the lab.
So what does this all mean for us? The real takeaway here is pure operational ROI. If an AI can use its reasoning capabilities to help a physical lab reach the absolute optimal solution in half the time, or with half the number of physical experiments, it drastically reduces the overall footprint of the research.
The efficiency gains are massive.
You are trading a little bit of extra compute power up front to save massive amounts of chemical waste, electricity, and real-world time. Machine reasoning isn't just some parlor trick for generating emails anymore.
Definitely not.
It is capable of dynamic, step-by-step scientific discovery. It outperforms strict mathematical guessing. It can recover from human sabotage, and it can actively navigate the messy, unpredictable realities of a physical laboratory.
That is the crux of the preprint. We saw throughout this study that the AI succeeded primarily because it possessed a human-like ontology.
Right, it had context.
It understood our world. It understood the semantic meaning behind the variables. It knew what a dye was. It knew how a salt behaves. But I want to leave you with something to mull over, something that extends far beyond the boundaries of this specific paper.
I'm ready for it.
If these models are already reasoning their way out of human errors, identifying when our hypotheses are wrong, and catching our outdated literature, what happens when the AI starts creating its own scientific categories?
What do you mean by its own categories?
Right now, it relies on our words. But what happens when an autonomous AI discovers relationships in the physical world that humans don't even have words for yet? Concepts that don't fit into our current understanding of physics or chemistry.
Oh.
We rely on it understanding our ontology today. But are you ready to collaborate with an intelligence that might soon have to invent an entirely new language just to explain its discoveries to you?
That is a wild thought to end on. An AI that has to teach us the physics it just invented because our language isn't big enough for what it found. Thank you for joining us on this deep dive. Keep asking questions, keep failing fast, and definitely keep challenging the established literature in your own life. We'll catch you next time.